Analysis of algorithms. We're going to begin with analysis with time complexity, asymptotic notations, big O notation, growth of orders, and some problems which we'll solve later. So the analysis is the determination of the amount of time, the storage on other resources that are necessary to execute them. Analyze algorithms is called also asymptotic analysis. Asymptotic analysis evaluates the performance of an algorithm step by step. Now, with time complexity of an algorithm quantifies the amount of time taken by the algorithm. We can have the big three cases to analyze an algorithm: worst case, average case, and best case. So since this is an algorithm using the Python pseudocode, we have created a function with two parameters, array and x, and declared a for loop for in range with the length of array, how much will be the array, and the condition if array of in the for loop e will be equal to x. Then we return the e plus 1, so we will increment it. Then we will return minus 1 because we start from 0 and we don't want to start all over again. This is the worst case analysis. In the worst case, we calculate the upper bound on running time of algorithm. As you'll see, we have created also a search function with the parameters array and x, declared a for loop for in range in the length of array, and the condition is the array of e will be equal to x, and return e plus I with incrementing it, as I said before. The worst case analysis is the case that causes the maximum number of operations to be executed. We also have linear search, which is the worst case, where it happens the element to be searched is not present in the array. For example, if you search for 9 or 8, which is not there, this is the worst case for the algorithm to find it. Also, we have pseudocode when the x is not present, and the search functions compares with all the elements of our array one by one. As you can see, as if the Python pseudocode said before, what would happen if the x would not be found there. And the worst case time complexity be big O of n. The average case analysis will take all possible inputs and calculate computing time for all the inputs. As you can see from the function, if we would have the number which would be there in the middle, or in the best case the first element. Best case, we calculate the lower bound or running time of an algorithm. The base case time complexity of linear search would be big O of 1, which is constant. Now the best case analysis is the case that causes the minimum number of operations to be executed. For linear search, the best case occurs when x is present in the first location or the first index. So in the first index is 0 and is the number for us is number 2. And this, in the best case, would be big omega of 1. Most of the time we do worst case analysis to analyze algorithms. Their average case analysis is not easy to do in most of the practical cases, and it is rarely done. The best case analysis is bogus. Guaranteeing a lower bound on an algorithm doesn't provide any information. Also, we have some asymptotic notation which you should learn it. We have big O notation, which stands for asymptotic notation for the worst case. We have the omega notation, which stands for an asymptotic notation for the best case. Of course, we have theta notation, which is for the worst case and the best case sometimes. It depends on the function which we have declared and the for loops and the if and the returning statement. Now big O notation. Big O of 1 is the complexity of a function or a set of statements considered as big O of 1 if it doesn't contain any loop, recursion, and call to any other non-constant time function. For example, the functions you can see in the illustration, swap function has big O of 1 time complexity. It's constant, as you can see, where we have declared a function with two parameters, and then we have returned the two arguments, s2 and s1. And a loop of recursion that runs a constant number of times is also considered as big O of 1. For example, this following function loop is big O of 1. As you can see, the c is constant. We have declared c as constant. And the for loop for in range from 1 to 4. As you can see, the result will be 1, 2, 3. And we have to print it. Big O of n. The complexity of a loop is considered as big O of n if the loop variables is incremented or decremented sometimes by a constant amount. For example, the following loop statements have big O for n time complexity. As you can see, if we declare n as a variable and c as the increment, for in range for e constant and variable c increment, and we can declare some big O of 1 expressions and print it is the e, which is the loop. Now this is the big O of n. Also, we have positive integer constant for int e is equal to I, with the condition if e will be less or equal to n, and then will be incremented by the c. And then we have some big O of 1 expression, which should be constants, don't forget. And another for loop, which is not nested loop, is another for loop. Doesn't have any connection with inside of it with the nested loop. It is outside, as you can see from the brackets. Declared another for loop for with integer I is equal to n, where I is greater than 0, and then we decrement it with the c. And of course, there's some big O of 1 expressions which are constants. Big O of n in the power c is the complexity of nested loop is equal to the number of times the innermost statement is executed. For example, the following function will have big O of n squared time complexity. As you can see, we have four loops in nested loops now. N is variable and c is increment. For in range 1 is constant, n is variable and c is increment. We do some the big O of 1 expressions, and then we also declare another for loop inside the first for loop. This now is the nested for loop. For j in range, constant of 1, n and c, in which n is variable, c is increment. We declare some big O of 1 expressions, and we have to print it the for loops, which is r and j. So we have another example for int e is equal to 1 constant. For if in the condition if e is greater or equal to n, less or equal to n, if e, and then e will be incremented by c now. And we have another nested loop in j is equal to 1, j is less or equal to n, and j will be incremented by the c. We have some big O of 1 expression, constants, also the same, but now we have the e is equal to n with an integer, e will be greater than 0, e will be incremented by c. And now we have another nested for loop for int j is equal to e plus 1, which will be incremented now with a plus 1, j is less or equal to n, and the j will be incremented with c, and some big O of 1 expressions there. Of course, we have big O of log n. The time complexity of a loop is considered as big O of log n if the loop is variable, is divided or multiplied by a constant amount. We have I as a constant, n is variable and the c is constant too. So we've done a while loop. If I is less or equal to n, we have to print I, and then we have to increment it with a multiplication c, multiply with the number, with the constant c, number c. We have another example for int is equal to 1, int is less or equal to n, and then we have to increment it with the multiplication sign times c. We have another for loop, int is equal to n is greater than 0, e will now be divided with a c each time. And some big of 1 expressions, which are constants. Of course, we have big of log n. The time complexity of a loop is considered as big of log n if the loop variable is reduced or increased exponentially by a constant. As you know, n is variable and c is constant, e is equal to 2. While e is less or equal to n, we have to print e. And now we have to increment it with exponentially with a double star sign. E is equal to the I double star sign c. This is increased exponentially by a constant. Now, as you can see, we have some built-in functions which we will use for int is equal to 2, int is less or equal to n, is equal to the power I, and the c, which is now will be risen exponentially. Now I have some big of 1 expressions. Also, fun is a square root or cube root or any other constant of roots. We have for int e is equal to n, e is greater than 0, e will be fun of e, which is a square root or cube root or any other constant root. And we have declared some big of 1 expressions. But how do we combine time complexities of consecutive loops? Now, nk is variable. For e in range of n, we have to print e. For j in range of m, we have to print j. Time complexity of both the code is big of n plus big of m, which now we can see is big of n plus m. So we have some growth orders. As you can see, with the n variables is 1, 8, 30, 500, 1000, 16 in 10 times 10 to the power 3, 1 times 10 to the power 5. We have big O of 1, which is all constants. Now we have big O of log n, 0, 3, 5, 9, 10, 14, 17. This is the way how they are grown. Each loop, each time they exponentially grow or are incremented. We have big O of n, 1, 8, 30, 500 is the same as n, 1000, 16 times 10 to the power 3, 1 times 10 to the power 5. Now we have big O of n log n, which is 124, 150, 4500, 10 times 10 to the power 3, 224 times 10 to the power 3, 17 times 10 to the power 5. Now we have big O of n squared, 164, 900, 25 times 10 to the power 4, 1 times 10 to the power 6, 256 times 10 to the power 6, 10 times 10 in the power 9. We have now big O of 2 in the power n, which now is incremented by 2, 256, 10 times 10 in the power 9, 3 times 10 in the power 150, 1 times 10 in the power 301. Because we don't have any more, because they are really large numbers now, so it will be really hard and to be executed by the program. Now big O of n factorial, we have 1, as you can see is 40x, now we have risen exponentially in the times 10 in the power 3, 210 times 10 in the power 32, 1 times 10 in the power 1134. Now we have 4 times 10 in the power 2567. You can see for the graph, you can see big of 1 is constant, big of n in the power n is really fast. We have big of n cube is also faster, big of n square, big of 1 is linear, big of O in square root of n, which is way faster than log n. Now we have big of log n, and big of 1 is really fast because it's constant. We still have the length of input and the word success algorithms now. We have to find the complexity of the below problem, as I said before, some problem solution. We have declared a function with integer n as a parameter. Now, if n is equal to 1, we have to return another for loop. We have to return, and now we have another for loop. For int e is equal to 1 is less or equal to n, and we have to increment e now. And the nested for loop in j is equal to 1, j is less or equal to n, and increment j now. And we have to print the star sign and break. As you can see, if you will execute in Python, we will have a data structure with a star sign, which will look really cool. Try it if you want. Now we have to find the time complexity, of course, big of 1, even though the inner loop is bounded by n, but we have the break statement now, and it's executed only once. Now let's create another void function in the integer n. Int count is 0 now. For int e is equal to n is divided by 2. E is less or equal to n. Now we have to increment I. For int j is equal to 1, j plus n over 2 is less or equal to n. And after j will be incremented with j plus plus. For int k is equal to 1, k is less or equal to n, k is equal to k times 2. And now we have to increment the count. Now, as you can see, this is a lot for loops will be executed, and now we have big of n square log n. As you can see, the complexity of this program, we have to declare a function with the parameter int n. The int count is 0. E is equal to n over 2, e is less or equal to n, and increment I. Int j is equal to 1, j less or equal to n, j is equal to 2 times j. Int k is equal to 1, k is less or equal to n, k is equal to k times 2. Now to increment count. This is the time big of n log n square n. As you can see, we execute big of log n times with a j now, and now we have to execute again big of log n times the k times 2. This is why we have a time complexity of big of n log square n. We have another problem. We have declared a void function with the integer n. The int count is equal to 0, and for loop with int e is equal to 0, e is less than n, we have to increment I. We have another for loop, int j is equal to 1, j is less than I times I, then we have to increment j. We have put an if condition if j, the percentage, if you can see, we will check it if it is negative or positive. This is called the percentage I is equal to 0. Then we have to do another for loop in k is equal to 0, k less than j, and we have to increment k. We have to printf the dot star sign. As you can see in the program, it look like a triangle now, and which would look cool. You can try in Python or in any online compiler. As you can see, because we have two for loops and if conditions and another for loop inside, which is incremented by k, j, and I, with some conditions where k is less than j, j is less than I times I, and I is less than n. Of course, this is kinda harsh to execute with the program for the computer. Even though we have did it directly, the solution was big of n in the power 5. But it look cool, and for the most of algorithms or data machine learning, we don't even care about these times. So thank you for sticking out with me these times, and hopefully see you again.